Well, thank you all for joining us, and I'm happy to be doing this with this great group of people that I've worked with in some cases, as David said, for a long time. What I'd like to do is sort of walk through the historical evolution of resource adequacy, and I think it's really important to do that because a lot of what we are doing today, certainly in terms of policy, is really grounded in the historical view of resource adequacy. So I think it's really important that we understand where some of these things have come from, so that we understand something about the evolution that we need to go through, not only with the power system, and we're certainly in the process of doing that, but Derek will talk a little bit more about kind of where we need to go in terms of how we think of resource adequacy. So this is kind of a brief outline of what we'll be looking at: historical assessments. Renewables are changing things. That's probably obvious, and one of the reasons that we're all here. There's some emerging interest in, I'm going to call it portfolio effects, but we'll talk about this a little bit later. But the idea is that the existing framework needs to be stretched and changed a bit to account for wind and solar. Talk about the impact of transmission and long-term weather, and certainly the latter is on everybody's mind following the February events in Texas and the Southeast. And then I want to kind of close with a bit of discussion of the gap between what the models are able to do and what we are generally doing in the sort of the decision-making framework in this country and even around the world. This slide is a reference. I'll ask you to kind of put it in your mental back pocket here for a few minutes, but I want to emphasize the structure of the US power grid. Now, this is a diagram. You may have seen other versions of it. This particular one is broken down by the reliability areas in the US. The important part of this is that on the left, you see the green states and provinces in Canada. This is the Western interconnection. And even though there are certainly transmission constraints between areas within the Western interconnection, all of these utilities, California ISO, are all connected to each other, some with stronger connections than others or weaker connections than others. And in the middle, you see the Eastern interconnection, essentially the rest of the United States and part of Canada, except for Quebec. And so we have this giant portion of the US on the right that's in the Eastern interconnection. And again, not all of these regions have strong connections with their neighbors, but they generally have some connection with the neighbor. So let's put that in our collective back pocket. We'll see that again shortly. So what about resource adequacy? As Debbie said, this is really the idea of saying, do I have enough stuff? Have we built enough stuff so that we can provide demand at some future date or maybe a future couple of years? And this sort of analysis, resource adequacy, can be done at any number of levels. The RTO, it can be done within a utility's integrated resource plan or energy plan. It can be done by various regions, but essentially we want to know if we have enough stuff built, and if we have, great, but if not, how much more do we need to develop or build or contract for so that we can make it through the future year or years that are the subject of our study. And we usually turn this upside down. Instead of saying, is everything really great? It's actually easier to do the analysis if we figure out how many problems do we have? Do we have any problems? And inquiring minds want to know, well, if I've got a problem, is it one problem or many? Did they last for a few minutes or a few days or, heaven forbid, a few weeks? How much energy was lost? How large was the capacity deficit? So these are all questions that we can think about when we turn this reliability, this resource adequacy issue upside down. How many problems do we have? How frequent are they? And so forth. So There's some other questions that we have to ask ourselves when we're doing a resource adequacy analysis. Are we concerned only with resources, generation? You can put demand response or dispatchable demand in that. Do we want to include the resource base plus transmission? And if we do consider transmission, what about the neighbors that are potentially able to help us during an emergency? And then we get into this is the policy question. So what is an acceptable resource adequacy target? Debbie mentioned the 1 day in 10 years, which is sort of the ubiquitous target. As I'm going to point out shortly, nobody really knows where that came from, but we use it. We use it anyway. It's a nice number. But from a policy perspective, we need to ask how many loss of load events per year or per decade are acceptable. How long is too long for one of these events? And we haven't really thought through that, I think, carefully enough in the United States and probably around the world, because we're sort of stuck in the historical 1 day in 10 years or some variation of that. And I'm not saying 1 day in 10 years is wrong, but I don't think we've really done sufficient justification of that, or maybe there's a better one. And the bottom line here is that you can always get more reliability. You can always build more stuff, but of course that comes at a cost. And so reliability isn't free. And so when we think about how much reliability is enough, or again, flipping it upside down, how many problems are more or less acceptable, we have to recognize that there is this trade-off between reliability and cost. And that's why the resource adequacy target, whether it's 1 day in 10 or something else, is really a policy question. How much are we as consumers or as a society even willing to pay to have a reliable system, however we might want to define that. The traditional approach to resource adequacy has often been based on a measure of installed capacity and peak load and a planning reserve margin. I'm not going to trudge through all those numbers, but this strictly speaking isn't really a reliability measure at all, because it doesn't address the issue of how often, how big are the failures, and so forth. And it doesn't really work very well without significant changes to a high level of renewable energy. So then we start asking these questions. Well, how reliable is reliable enough? This 1 day in 10 years target that is often used more or less translates to 99.97% of the time everything is okay, and that's pretty good. And that we often measure as a probability that demand will exceed supply. And of course, we need to think about how we're going to treat demand response when we do the math. That's doable, and we'll talk just briefly about that a little bit later. On the right, you see some kind of sample, what we call forced outage rates for different types of generating units. And this is the data that's utilized to help calculate the loss of load probability. For any given resource, a coal plant, a gas plant, you name it, there's some probability that it's going to fail. And those failures can happen within a fraction of a second. And we need to make sure that the power system can survive those kinds of things. So I just wanted to put these up here to show you that we have a lot of data that goes into these loss of load probability calculations. And a lot of it depends upon the types of resources that you have. So back to that back pocket picture, I've been talking about loss of load probability, but in fact, in most of the US and in many places in the world, it isn't really a loss of load that we're measuring. We're looking at the probability of an emergency import from the neighbors. Now, that emergency power may or may not be there. We don't know what's happening on the other side of the meter. But the point is that oftentimes, if we are in some sort of an emergency, we do have this large interconnected system, particularly in the East, but also in the West. And we can often draw upon neighboring systems to help out and deliver some emergency capacity and energy. And if that can happen, then we're not truly talking about load shedding or dropping load. we're talking about some sort of an emergency import from the neighbors. And how to quantify that is a difficult thing, and we'll talk just briefly about that a little bit later as well. So this diagram is actually taken from a paper written in about 1950 that talks about the idea of using probabilistic analysis to start looking at resource adequacy. And this is important because this is kind of where the 1 day in 10 years target came from. Back in the 50s, actually some of the really early calculations, and this makes my head hurt to think about it, they're using desktop calculators. So you imagine these giant sort of typewriter things with numeric keyboards, and it must have taken an army of people days to calculate a simple loss of load probability. But so computation was really difficult. And then eventually people moved to punch cards on computer systems. And if you don't know what that is, you can probably look that up someplace. But the computing power was extremely limited. And so what folks did was they said, we're going to take the peak demand from each day. So that's 1 hour per day. We're going to throw away all the weekdays because generally demand during the, we're going to throw away all the weekends, throw away all the weekends because demand on the weekend is generally a lot smaller than it is during the week. And we want to also eliminate weekday holidays. So when you do the arithmetic associated with how many values per year, that works out to be around 250 demand values per year. And then we're going to use that to calculate a 1 day in 10 loss of load probability. So when you think about that, it's about 3% of all the data points in a year that we're going to use to try to figure out if we're adequate or not. This is some of the evidence, 1950, 1951, even back to 1947, when some of this work began. Back in the 1950 paper, Calabrese said, we don't really know what a target is, but 1 day in 50 years loss of load should be satisfactory. That's really reliable. There's nothing wrong with that, but I'm not sure we want to pay for that. But think about the fact that when he's doing that assessment, it's 1 data point per non-holiday weekday that's being utilized. A couple of quick terms. Probability is a number between 0 and 1 inclusively. I used the example of flipping a coin, a penny here. If I want to look at the probability of flipping a head, assuming it's a fair coin, it's a 0.5 probability, and therefore a 0.5 probability of flipping a tail. The expected value of the number of heads I get is a little different. And so if I say I'm going to toss a coin 100 times, and I want to find out how many heads I'm going to get, I can calculate the expected number of heads, number of tosses, 100 times 0.5, which is the probability of a head, and we can calculate that I get about 50 heads. We have the same sort of terminology in the power system. A loss of load probability, strictly speaking, is between 0 and 1 inclusively, and a loss of load expectation, it's sort of like those 50 heads, that's the expected value of my loss of load. And we often express that in terms of days per year, 0.1 day per year, or 1 day in 10 years, or something like that. There is a memorandum by a guy, I believe he was at GE, that talked about, that sort of came up with this analogy of rainfall and what's the probability of raining during the day and so forth. I won't go through that, but this is really some of the first evidence that people started thinking about a 1 day in 10 years loss of load probability. So renewables come along and things change significantly. Back in the old days, before renewables, most of the loss of load risk was during the peak or the near peak times. With renewables, we have shifting risk periods. We also want to think a little bit more about those other 23 hours of the day and those other 300 and some odd days of the year that we ignored when we looked at holidays only, or non-holidays and weekdays only. We do have a lot of tools that can help. And Derek, a little bit later, is going to be talking about ESIG's redefining resource adequacy. But as we start thinking about renewables, we want to know sort of how they contribute towards a reliable power system. Now, this measure, you may have heard of effective load carrying capability. I want to point out that this actually came about in the 1950s and in the 1960s. And this is long before wind or solar was, anybody was taking it seriously. You often hear folks today in the industry, in the power system industry, saying, well, we've got all these things we're going to do for thermal units, but oh, here's wind and solar, they're special. We're going to use ELCC for wind and solar. That doesn't make sense, because in fact, ELCC was really developed for baseload resources. And we have adapted that to renewable resources. And I'll just take a minute to go through this. If we have a reliability target as represented by this red line, 0.1 days per year, we have a bunch of generators. We build out the system. You can see the gray lines moving to the right. And if we're at 0.1, we have meet our reliability target at a demand of around 10 gigawatts of load. But now if I add a new generator into the system, this whole blue reliability curve shifts to the right. And what we want to do is essentially measure the horizontal difference between 0.1 and 0.4. And that tells me how much additional demand, 400 in this example, how much additional demand can I meet at the same level of reliability. We call that effective load carrying capability. And so you'll often see folks talking about wind ELCC or solar ELCC. This is what it is. And to calculate ELCC, you need a reliability model or some sort of production simulation model. You need hourly demand in wind and solar and hydro, the forced outage rates that I mentioned earlier. I would have multiple years of time synchronized data. In other words, because weather drives demand, weather drives wind and solar and hydro, we want to make sure that the data is all consistent. So we run the LOLE model a number of times, and I don't think it's critical that we understand exactly how we do that, but that gives us essentially the LOLE for, the LOLE for the system, but also the effective load carrying capability for wind or for solar or for hydro or whatever resource we're looking at. So when wind shows up, and solar is a little different, but it changes how things work on the power system. This is a sample of demand you see in the red. This is actually 1 week of data. And this is data, I think it's from a Minnesota study that we were involved with 10 or 15 years ago, looking at a large amount of wind in the state of Minnesota. The wind is shown in the graph as green. And if you take the red, which is demand, subtract off the green, you get net demand. And so the idea here is the blue represents what we call the net load or the net demand after we've accounted for all the wind. So we do this because in the power system, if I can make the best possible use of all this wind, I mean, it's free energy. Once I built the turbines, the wind blows and it's essentially free. I can now turn down my gas and coal and whatever else I have on the power system. And now the net demand that I need to meet with my hydrothermal system is this blue trace. And you can see that the pattern of blue is pretty different than the pattern in red. Over here, hour 1310 or whatever it is, you can see the pattern doesn't change very much. And if you drop down to the bottom, you can see that's because there wasn't very much wind in those hours. So the wind didn't change things all that much. But if you go back to hour 1220, where you see that steeper ramp, there are a lot of things going on, but the wind has really caused you to be able to turn down your thermal generation quite a lot. And so, wind doesn't behave the same way every day or every year for that matter. And so you can then sort of take a look to say, well, what is its contribution, easier for me to say, what's its contribution to the peak demands for this week? And from this example, we can see that it's kind of all over the place. And that also tells us that the risk profile is going to be changing. What are we having loss of load events or probabilities? It used to be right around those top red peaks, but now it may be around some of these blue peaks. And then when we add solar in, it gets even more complicated. This is just a kind of a quick example of a range of capacity values of wind and solar in the West. I won't spend a lot of time to go through this, but you can see that the ELCC of solar varies around the West, probably no surprise, anywhere from 60% down to maybe 30% in California. ELCC of wind in the West also varies significantly. California South and the Rocky Mountain areas, 10%. I mean, it depends on what year of data we're looking at. We were looking at a fairly high penetration, I think, when we ran these numbers. California North and British Columbia are very different. So there's really no one size fits all. You've really got to do the math for the specific wind site or combination of sites that you're looking at. And you've got to do it for the specific region of the country, utility, and so forth. Wind and solar capacity value, ELCC, depends on a whole bunch of things. There's been a lot of attention lately given to the impact of the penetration rate on capacity value. So Debbie showed the sort of ubiquitous duck curve a little while ago. The more solar you have on the system, the less other stuff you need in the middle of the day. And so that shifts the risk. And so we can see here that the capacity value of PV, the energy value of PV, it all tends to drop as the penetration goes up. But there are a lot of other things that the capacity value depends on. The capacity value will depend on forced outage rates of your other resources, gas, coal, whatever else you've got. It'll depend heavily on the storage that you have and how you're operating the storage. That includes pump storage. Maintenance schedules can play havoc with not only ELCC, but also risk profiles. You think about back in the old days before a lot of wind and solar, October might have been a good time to do a whole bunch of scheduled maintenance on your thermal units. And so, if everybody goes out and does maintenance and you don't have much wind or solar in that month, you could run into some trouble. Imports and exports drive this, as do hydro generation patterns. So when you do an ELCC study for any resource, PV, wind, it depends upon everything else in the system being held constant. And we know that isn't really true. And so I think there are some shortcomings, and Derek may be talking about some of this with respect to how we look at ELCC in the future. Storage and demand response have a big impact, and no surprise here, the effective capability of storage also declines as you get more of it. And the same thing is true with demand response. But we do know how to do the math for this now, and I think as we see increasing levels of storage coming on the system and demand response, and of course solar and wind, we need to be really careful about how we treat all of these in the calculation. There's an emerging interest in this so-called portfolio effect, and the idea behind this is that we know the capacity credit drops. This particular graph is PV from some work that Andrew Mills and Weiser did almost 10 years ago now. But what this shows is a number of different studies that you can see here in the color coding legend. And as I pointed out earlier, all plants are a little different, but you do see this characteristic of a declining capacity value for PV as you add more and more PV to the system. And this portfolio effect is sort of the idea of saying, well, rather than looking at this as each individual PV resource, whether it's utility scale or perhaps even distributed, think about how the overall portfolio of solar contributes. And the E3, the consulting company in California, has been doing some thinking about this, and others have been thinking about this. to try to get away from strictly the ELCC of the last plant that you build to talk about the ELCC of the solar portfolio. And you can see that there's a sort of the first in contributions a big number, the last in contributions a low number, but the solar collectively is doing a lot to help with reliability of the system. The other interesting thing that happens with ELCC is that you can get what we call a diversity benefit. E3 also talks about this, and I think it's a really important point that if you look at wind by itself or storage by itself or solar by itself, you get different ELCC values. And so there is this diversity benefit that we need to be capturing when we look at the overall system. Wind and storage together, I won't spend a lot of time on this one, but this shows some of the differences that you get in the capacity contribution of wind by itself. I think my slide may be mislabeled there, but no, sorry, wind and storage, and the diversity benefit that can be calculated from a model such as some of the ones that E3 uses. One of the biggest issues in my mind is weather, and of course this is, we're all thinking about what happened in Texas and the Southeast and even a little bit north of there in February. How does weather affect renewable energy? Well, we know it affects it a lot, and I won't drag you through all these slides at the bottom, but in fact, when we get something like the graph, or the map that you see on the west, we have an extended Pacific jet stream. It's low in the wintertime, and it brings down more warmer weather. That can also cause a relative lack of wind in the upper Great Plains, Minnesota, Dakotas, and so forth. And so you want to take that into account when you're doing your planning. We actually, the bottom left two graphs, and I won't go through all the gory details, but we had a year, 1996 and 1997, ancient history here, where the jet stream actually split. So part of it was going where you see this orange track, and the other part was going north of the Dakotas into Canada. And so that created basically a wind drought in Minnesota, Wisconsin, the Dakotas, in that area. But depending upon what's happening with El Nino, La Nina, the jet stream, over here on the right, you can see colder, wetter weather, which generally brings the wind, and of course, you generally get less solar. So we need to really be careful about how we address weather as we go forward. And I think that's one of the real weak links. It's not a weak link in LOLE analysis, really. It's really the data itself that is more the issue. So that kind of takes us all the way back to the beginning. What is an appropriate reliability or resource adequacy target? There isn't any particular justification for 1 day in 10 years. We've been using it for a long time. It's a nice number, but it doesn't really give us very much information that's useful in terms of the length of the outage, the depth of the outage, how much capacity. We need to be careful about how we treat imports from the neighbors during emergency events. When you think about 1 day in 10 years, the way we've sort of historically measured it, there's really no difference between a 10,000 megawatt outage for 23.5 hours and a 100 megawatt outage for 1 hour. And clearly we would like to differentiate between those. And so I think a lot of work needs to be done to try to figure out at sort of the policy level, what is it that we want? What are the acceptable targets? What are people willing and able to pay for? And how do we roll that into resource adequacy calculations? Transmission adds another whole level of complexity to the issue. On the left, you see a graph that I adapted from some work we did at NREL a long time ago. It's the Eastern Wind Integration and Transmission Study. And there are a bunch of different scenarios, but what I want to point out here is if you look at the left-hand two bars, there's a brown bar, and that was the wind ELCC, just over 15%. We kind of rolled this analysis into MISO's transmission expansion planning, and when you applied the transmission expansion plan, the wind DLCC, same amount of wind, same place, went from around 15% to 26, 27%. You see the same pattern occurring throughout all those scenarios. What that means is that transmission can actually help with not only integrating wind, but on the right-hand side, we did some kind of follow-on work of this at NREL to say, well, in the Western interconnection, could you actually reduce building a bunch of capacity if you had a better transmission system? And the answer there is yes, you can. And this graph shows for different levels of wind and solar, wind and solar mixes, different levels of aggregation. I think the maximum case, we had a lot of wind, we had a lot of solar, we could actually reduce capacity in the West by around 50 gigawatts if we had a perfect transmission system. Now, I'm not going to argue we're ever going to get anywhere near perfect, but what this shows is that some intelligent transmission design can actually result in building less resources, whether you're building wind or solar or batteries or gas or anything else. So what do we have to do? We've got to integrate resource planning, transmission, and distribution planning. And I'm going to go through each of these in a little bit more detail in a moment. We need to focus on energy first planning. We need to think a lot more about long-term weather impacts. We need to rethink our metrics and our targets. What is it that we really want out of the power system design? We need to make sure we can incorporate dispatchable demand or DR and storage. We need to close the gap between what we know how to model today and our decision-making processes. Incorporating transmission and into resource planning is not a simple thing. I won't go through the gory details of this flow chart here, but the basic idea is that when you build transmission, that affects the power flows, and you need to take a look to see if you need to change something on the transmission system. When you add new transmission, that changes where things flow, obviously, and that may mean that you don't need to build as much generation. So basically, you've got an iteration here. Build transmission, take out generation, build generation, build or take out some transmission. And so a flow chart like this one can be used to help kind of inform this joint planning of transmission and resources. But that doesn't really go far enough either. We really also need to take into account distributed resources. We see this huge increase in rooftop PV in the United States, and we're going to be seeing more batteries that go along with that. And that really should be a part of our system planning. As hard as that is to do, we need to start figuring out ways to do it. Hawaii is figuring it out. It's a small system, it's a unique system, but I think we can learn some things from what's being done there. Transmission planning is a huge challenge. We know that if you build transmission incrementally, you say, well, next year I need this transmission, assuming you can build it. Let's build this 138 kV line from A to B. Well, 5 years from now, that line's too small, and then you're going back to reconductor it for a higher capacity. We want to avoid that, and yet we want to size our transmission in a way that's appropriate and also going to work in the long term. And Texas has had the competitive renewable energy zone process for a long time. Seems to be working reasonably well. It's not perfect, but it's an idea of being a little bit proactive about where and how we build transmission. Energy-verse planning is sort of this idea of turning the tables. Instead of thinking about capacity first, we think more about energy. And so sort of hypothetically, think of a triangle as all of our energy needs. Capacity is sort of buried in there, but fill up the triangle to the extent you can with renewables and dispatchable demand, and then figure out what else you need around that. Is it storage? Is it more DR? Is it quick start thermal? What is it that we need to put in that other triangle? But we can start with looking at our renewables to figure out what they're going to do based on your state's goals and region goals and so forth. Weather. It's the meteorology. I won't go through all of this, but you can sort of meditate on this slide, and it's probably obvious in many ways that weather drives everything we do in the power system. It's driving demand. It can drive resource outages. It certainly drove a lot of interesting things in Texas a couple of months ago. But even without extreme weather, we've got NOAA, for example, just I don't know, a week or two ago, released the sort of the new normal, if you want to call it that, the new temperature norms, which are a couple of degrees higher than they've been over the last period of time. So now when you say the temperature is higher than normal, normal is also higher than normal. And we need to really capture that a lot more robustly in our planning. You've got a weather year that's so above average or so cold. We do a lot of utility planning based on a representative weather year. Maybe not an average weather year, but a representative year. But what about the representative years that start looking at unusual representative heat waves, representative cold waves? We need to do a much better job of capturing that in our planning. We need a lot more work on metrics. I've got this simple example of two different events. Each counts as a loss of load event, but they have different energy, different amounts of energy spilled, different levels of hours. But if you're doing a simple 1 day and 10 year, they both get counted in kind of the same way. So we need to be a lot smarter about how we do some of that stuff. There's lots of metrics, and this is just some kind of off the top of my head, so to speak. We have models that can calculate loss of load hours, how many hours you've got a problem. We can calculate the loss of load expectation. We can measure it in days. We can measure it in hours. Something else, perhaps. We can count the number of events. We can keep track of the average length of the event, the maximum length of the event. We can calculate the expected unserved energy by event, average by hour. All of that stuff most models can calculate that pretty well. Policy, we're stuck either in a planning reserve margin mode, or sometimes we have a 0.1 day per year, or 1 day in 10 years, LOLE. We often use a single year of modeling, single year of weather. Maybe that's been okay up to now. I'm not sure it has been, but we really need to sort of break down this big black wall I have between the models and policy. But there's a lot of thinking and policy making that really needs to go into this. I've got just a couple of minutes left. I want to kind of walk you through this animation that hopefully is going to work here in a moment. This is an example of using demand response to provide regulating service. Regulation is an ancillary service that's generally done every 4 seconds. A bunch of computers are figuring out exactly what the demand is. It goes up 4 seconds, goes down 4 seconds, and then the computers send a sort of a ping to a subset of the generators to move up or move down so that we can match that short-term variation in load. So what you see on the lower part of this graph is a red signal, which represents the AGC from roughly 6.5 hours. And so this is what the utility needs. And up at the top, we have what we're going to be seeing here in the animation in a moment is we're going to step through a bunch of discrete resources that can be added, demand response resources, compressors, pumps, and so forth. And each of those devices will interact as like a block. And you can see this green off-on block, and you can see this sort of this tan off-on block. And so each individual resource is going to behave like a kind of a block, if you will. But we're going to assemble all of these together so that we can get really close to that red line. So here's the animation, and it's just going to keep running here. But and I know you can't see all the gory details, but we're adding these various devices one at a time in that blocky fashion, and eventually we get awfully close to the AGC signal. Now, why do I show this? We could do a lot with demand response that we haven't yet done. We the example I showed you is regulation. We need more than just regulation from demand response, but what that example shows is that not every resource has to do everything. You can have a bunch of blocky response from a bunch of resources, and you can compile those together in such a way that you can get a lot of interesting shapes. And of course, the shape of interest is really that net demand, that net load after we count for wind and solar. And so the question is, how many ways can we mix and match various demand response capabilities in a way that can help us with the system? So what we really have to do is close this gap here between modeling and decision making. The models can do lots of metrics, but the models don't know what what's sufficient level of reliability. That's where we need to come at this from a decision maker and a policy point of view. We need to get a lot smarter about that. We need to take multiple years into account. I'd like to close with some optimism. I mean, we somewhere, not just me, but across all of the brains in this industry and the models in this industry, we've got a lot of what we need already, but we need to apply it, and we need some guidance to figure out what sort of reliability targets do make sense. We need to develop a common framework, and I'm not sure if I mentioned this, I should have. This whole loss of load probability and ELCC, it's not just a metric, and it's not just a formula, it's a framework. And it's like an insurance company figures out risk, and we need to figure out risk in the power system. We need this framework, and maybe LOLE, LOLP isn't the right framework. I think it is, but we need to be able to push that forward so that it's changing, and we can change it in a way that we can get what we need out of the power system. We need to connect the tracks, and I think with that, I'm finished.